Welcome, everyone. We are into the next session. We are welcoming Ronnie, Ethan, and Andrew from Capital One. We'll be talking about observability and the works. So, thank you so much for coming.
Thank you so much. So good morning, everyone. Thank you so much for attending our sessions today. My name is Adi, and here with me, Ethan and Ronnie will be presenting for the topic today. So currently we are working as a data scientist in Capital One at ML observability space. So what we do day-to-day basis actually motivates us to present this talk today, which is holistic root cause analysis of software breakages through structural causal modeling. So this is the breakdown for our talk today. First, we'll provide motivation for our talk, defining what is observability and the importance of it. Next, we will also talk about the challenges that surrounds observability. Specifically, we'll talk about why root cause analysis of software breakages is really hard. Ethan will then talk about an approach called structural causal model and how this approach can be used to solve this problem. He will also provide an example through a simulated data on how we can use this algorithm in the real world. Lastly, Ronnie will talk about how we are able to combine different signals from the data in order to create a holistic approach in root cause analysis. So what is observability? Observability can be defined as the act of understanding the current state of our system. This includes gathering and analyzing telemetry data, such as logs, metrics, or traces, that is generated by components throughout our tech stack, be it from the infrastructure level, network, up to the applications level. The goal of observability is for us to be able to identify and resolve issues quickly. For us, specifically, when we are working at the banking industry, having issues within our applications can have severe impact to our customers. Therefore, having observability within our system is important, and not just us, like for every system that there are. What differentiates observability from monitoring is the emphasis of trying to understand why a certain component has failed. Monitoring system allows us to be alerted whenever any of our services are down. For example, we'll get alert whenever, let's say, our customer is not able to access specific page within our mobile application. However, it might not be obvious to what is the reason. Having observability allows us to know that, let's say, the issue is within a specific database. There is a read error into it, and thus the service can't make a call into it. There are a lot of Python and open source tools that is available out there that can help us to do this. One of them is OpenTelemetry, where it provides API and SDK for us to standardize our telemetry data such that it can be consumed and analyzed using third-party vendors out there. One of the issues in tracking different components within the tech stack is that each of them can spit out hundreds of different metrics, logs, and traces. These metrics will be different from one another because each components are built using different tech stacks and serves different purposes. This might translate to a lot of noise for the SRE team that is handling and monitoring the systems. Therefore, for us not to have any alert fatigue, there are 4 golden signals that can serve as foundation to understand the overall health and performance of a system. First is latency. Latency measures the time it takes for us to service a request. Thus, we can check whether there is any performance issues whenever a request takes a longer time than usual to complete. Second is response status codes. It allows us to get the rate of requests that has failed. So one way for us to track whether our application system is healthy or not is to check the proportion of client errors and server errors through the number of total requests. While occasional client errors or server errors are expected, spikes unexpected spikes or unexpected drops can signify that there is underlying problem within our system. Next, traffic. Traffic measures the rate of requests to our service. Understanding traffic patterns allows us to identify anomalies within our system whenever we see an unexpected drop or spike. And lastly, saturation. Saturation refers to resource utilization, such as CPU, memory, or I/O. So a system will usually degrade whenever the resource utilization nears full capacity. That's why monitoring saturation can help us to understand why an incoming request is being throttled or being rejected. Previously, we mentioned that root cause analysis is a big part of creating observability within a system. However, there are a few challenges in doing so. A lot of different teams have adopted microservice architecture within their system. However, this creates a dependency graph that grows to be more complex. As services are interconnected, it can be really challenging for us to point out where is the origin of the problem, as one service will depend on many services, and those services also calls numerous other services in order to complete their request. Also, some services will also use asynchronous communication patterns, such as message queues or event stream, in which makes the causal relationship between events more obscure. Lastly, as each services are being deployed independently, this might result in unexpected change of behavior, and it makes it hard to pinpoint the root cause of the issue. Also, even when we have managed to collect telemetry data, and we have managed to create our dependency mapping, it is still hard for us to reconcile all this data to perform root cause analysis. As the signal data have different patterns throughout the day, it might not be obvious for us to first identify whether there is anomaly within our service, and second, to pinpoint that this is the anomaly that caused the issue on the problem that we are investigating. As we are not only tracking different signals from one, but multiple components, this problem will even get more complex. Thus, we conclude that performing root cause analysis in microservice architecture is really hard. First, as services get onboarded and deprecated, at all given moment in time, we need to have a complete dependency map for our microservice architecture. This also means that the approach that we are using cannot use a lot of training data, as new services are onboarded daily, and it might not have a lot of data. Also, being able to perform RCA quickly is critical. As we mentioned just now, like downtime will have a lot of significant impact. Lastly, there is different data from our golden signals. So being able to monitor each services from a different angle is important to detect different kind of issues. A lot of these data, such as status codes or traffic, will have a lot of seasonality pattern with it. So our method should be able to consider this in determining anomalies at different times, let's say during peak hours or non-peak hours. So now I'll pass the mic to Ethan that talks about the algorithms.
Thank you, Adi. So yeah, this is the algorithm that we are using to solve the problem that Adi just set up. This is called a structural causal model, or an SCM. The way it works is that you represent the variables and the dependencies in a network as a directed acyclic graph. There's going to be three types of variables in your graph: the explanatory variables, the outcome variables, and the unobserved or noise variables. And you use machine learning to learn the relationships between those variables. So using this toy causal graph as a concrete example, we would say that node X here is the explanatory variable, node Y would be the outcome variable, and we would say here that Y has a causal dependency on X. So what that means is that Y would be some function of X and the noise or unobserved variable N. And just to reiterate, the goal for the machine learning is to learn this function f based on training data. The Python library that we use to create this model is called do-why. It's a really nice library for different kinds of causal reasoning tasks, causal inference tasks. It has an object called structural causal model for SCM, and it has built-in methods for both fitting these causal mechanisms and also for doing the root cause analysis, or what they call anomaly attribution. So the way that do-why works for the SCM, the goal is to learn the generative mechanisms for each node. So how does each node produce a value given the other values of nodes in the network, right? So looking at the root nodes, or those explanatory values, the variables, those are assigned a stochastic mechanism. We can empirically learn a distribution underlying those nodes based on sampling from the training data. Non-root nodes, or the outcome variables, are assigned what's called an additive noise mechanism. So the value at node I is defined to be some linear function of the parents of node I, plus, again, that noise or unobserved variable associated with node I. And those are these in the graph. So this turns each of those outcome variables into linear regression problems, basically, a series of linear regression problems, one for each node. And again, we can fit this based on the training data, and the do-why library has a number of built-in linear regression techniques that work under the surface to solve that problem for us. And then once we have that fully trained network, then we can do what they call anomaly attribution, what we're calling root cause analysis. The goal here is to use counterfactual reasoning to try and learn how much each upstream node contributes to a given anomaly. Right, so I've got a toy little graph here. Let's say that this node C is having an anomaly of some kind. We also know the actual values of A and B at the moment, and we can ask ourselves, if node A or node B had a different value, what would the value of node C be? And would there still be an anomaly if those values were different? So to go step by step through this algorithm, the first step is to compute a metric for the anomalousness of the anomaly that we've observed at node C, what they call an outlier score. And we can do this based on the probability of observing the value that we saw, the anomaly that we saw. We know the generative mechanism underlying node C as a result of our SCM training process, and so we know we can estimate the probability of seeing that value. Then step 2, we go one at a time through the upstream nodes, and we assign them a value that is normal for their underlying mechanisms, and we see how that impacts the value at node C. And in particular, we see how that impacts the outlier score, and most particularly of all, if that causes the outlier score to drop. And then finally, we use Shapley values to attribute the contribution of each upstream node to the anomaly. For people who are unfamiliar with Shapley values, this is a concept from game theory. If you have a collaborative game where everybody's working together, Shapley values can quantify how much each player on the team contributed to the goal. So if you think of these nodes as playing the anomaly game, where their goal is to drive up that anomaly score as high as possible, Shapley values translate really nicely to quantifying how much each node drove up that score. So let's walk through a really concrete example with this toy network. I've defined node A and node B to just be the roll of dice. So node A is a 4-sided die, node B is a 100-sided die, and node C is defined to be the sum of those 2 dice rolls. And let's imagine that we roll our dice and we get a sum of 2. We can ask ourselves which of the upstream nodes contributed most to this anomaly. On the face of it, you might think that they both contributed the same because they did both contribute the exact same value. But as we step through the algorithm, we're going to see that that's not the case. So step 1, we compute an outlier score for our sum of 2. I'm going to be a little lazy. I'm not going to deal with the probabilities. I'm going to look at the expected value, and particularly the difference between the actual and expected value. So the expected value for the roll of these two dice is 53. So a sum of 2 would have an anomaly score of 51. And then I'm going to go one at a time. I'm going to start by setting node A to its expected value, 2.5. I'm going to update the sum, 3.5, and compute the new anomaly score, 49.5. So a little better, making this change does cause the anomaly to reduce a little bit, but not to a very large extent. And if I do the same game with node B, set that to its expected value, all of a sudden the anomaly score drops all the way to 0.5. Now again, I'm gonna skip the Shapley calculation for simplicity, but I hope it's pretty clear that node B did in fact contribute substantially more to this anomaly than node A did. And in retrospect, I think this is actually fairly intuitive because it was much less likely in the first place for node B to roll a 1 compared to node A on a 100-sided die versus a 4-sided die. So that's the modeling technique we use and the algorithm for anomaly attribution. And now I'm going to walk through some of the experiments that we ran on simulated data just to sort of validate this approach before trying it in production on real data. We're interested in microservice breakages, so we started by creating a network, a simulated network of APIs that all have various dependencies, and they all pertain to some initial request. So you can imagine maybe this is a customer trying to log in, and that causes a whole cascade of API calls as one calls the other, calls many, all the way down the chain, and all the responses flow back upward. And you can imagine that if all we know is that people can't log in, if all we know is that there's an error over here, in principle, any of these nodes could be the culprit. Any of them breaking could cause that observation at the top of the graph. And so that's and just to reiterate what Adi's been saying, that's what makes root cause analysis so challenging. Now, one piece of bookkeeping before we move on is that we're less interested in the requests that each node makes to each other than we are in the responses that they get. Like you can imagine here, I'm looking at this edge between node 2 and node 4. If node 4 is breaking and is sending bad responses to node 2, then node 4 is going to have a causal impact on the behavior of node 2, but not so much the other way around. If node 2 is breaking, node 4 is going to be fine. So for causal reasoning, we actually flip the graph. This is the exact same graph, but all the edges have been reversed. Because this better captures the causal relationships. 4 has a causal impact on 2, and that's what this graph represents. And so just going forward, if I say that some node is downstream or a child of another node, what I mean is that the downstream node makes a request to the upstream node and receives a response in return. Might be a little backwards from the network flow diagrams you've seen before, but it's a necessary step for the causal reasoning. So the graph like that covers the dependencies, and now we also need to simulate that golden signal data that Adi was talking about before. So at each time step, every API will be associated with a certain average latency, a certain overall volume of requests, a certain distribution of status codes. So 2xx for success, 4xx and 5xx for different kinds of failures. And again, the key point is that these signals are going to propagate throughout the graph. Like you can imagine if a child API calls its parent, and we're talking about latency in particular, if a child API calls its parent and the parent has some latency, that child is going to be sitting there waiting for a response, and so the latency of the parent gets baked into the latency of the child. And similar things for successes and errors. So that's what I mean when I say that the signal propagates. And exactly how the signal propagates, like how much latency from a parent gets passed on to the child, ultimately that is an assumption that we had to build into our simulation. I'm going to mention this more later, but we ran these experiments under differing sets of assumptions. Those basically boil down to differing sets of experimental conditions. So we've got our graph data, we've got our dependency graph rather, we've got our golden signal data, and so now with this simulation, we can break it. We can introduce a failure somewhere in the graph, and we can see how those signals propagate throughout the graph. So we introduced, it looks like in this case, we introduced a tendency for this parent API to fail, and so now the child has some failures, but by 2 children down, it seems like that's mostly faded away, except in terms of the overall latency. This is just one example. And the goal for our experiment, the goal for our model, if we introduce a failure in the parent API, this is the one that we're considering to be the root cause. So even though there's all these other signals in the children, this is what we are hoping our model will identify. The end result is a graph that looks like this. In this bar plot, the higher the value, the more likely a given node is to be the root cause, according to our model. What's actually being plotted here are those Shapley values from the anomaly attribution algorithm. So again, higher value, more likely it is to be the root cause. In this case, this specific experiment, we added a few milliseconds of latency to API number 4 in that original network graph. And you can see that it really stands out as the clear root cause, just with a small addition of latency. And what we found through this experimentation is that under those different sets of experimental conditions, we are able to get good results. And we're also able to get good results at different, as we embed the anomaly at different levels of the graph. Like you can imagine if we put an anomaly very, very close to the initial request, that might be more of an easy case, whereas if we put the anomaly very, very deep in the graph, that would be a more difficult case. Despite those different setups, we are still able to get good results. With that, I'm going to hand things off to Ronnie.
Thanks. So this is not black magic. There are some assumptions and some data we have to work with, right? So this isn't a highly idealized example of what you can work with, right? So let's assume you have several thousand or 1,000 observations prior to some breakage that occurs. So these are observations on 2xx counts, 4xx counts, 5xx counts, the entire golden signal suite, right? We have that time unit by time unit. We have a sense of what that dependency graph looks like at the time of the incident. And you can play with that a little bit. I mean, depending on your organization, maybe the graph doesn't change dramatically week to week. Maybe it's just like a 1% difference as new features and new microservices are entered. That's okay. And then with this approach, thankfully, it only requires 2 to 5 time steps of data post-anomaly beginning. So you don't have to wait hours and hours to get data to understand what's the underlying root cause. And so in theory, if each time step here is 1 minute in length, aggregations of how many 2xx in the last minute, 4xx in the last minute, it could theoretically work in 2 to 5 minutes after a breakage. Could start that process of running the algorithm. How do we go about doing this in a holistic fashion? Well, I think there's a pretty simple, naive way to go about it. You could essentially run this model for each facet of the golden signal. So run the model for 2xx, 4xx, 5xx, latency, etc. And perhaps you could weight the ultimate scores by the severity of the anomaly you observed in each of those facets. And so what we've seen in a few examples is 5xx anomalies. When a severe breakage occurs, you see something like 10,000x increase in 5xx codes, right? So it's huge, right? 4xx, you might see a 2-fold increase. So in this particular example here, we would weight the 5xx scores by orders of magnitude more. It's a simple, naive approach, but it works reasonably well. I'm sure there are cleverer ways to do this, but as an initial step, it seems to be a good way to go. Yeah. Again, it's not black magic. There are some hard assumptions we have to take very seriously. So, in this simulation work, the problem space is massive, right? The engineering teams make APIs in so many different ways. And even status codes are used differently. In our organization, some people consider 403 code to be basically success. And they code their responses as such. Other teams consider their 2xx, which is a success response. Other times, APIs handle errors gracefully. and they don't propagate the errors. Sometimes they don't. Sometimes they just happily pass it along to the downstream one. So there's so many knobs to turn and so many levers to pull. It's hard to completely cover that problem space in the simulation. So we took our best shot at that. And it seemed to be reasonably successful across that landscape of choices. This is the Achilles heel here. You really do need a complete microservice dependency graph. Garbage in, garbage out. There's been some work demonstrating that by Patrick Lobaum, who was sort of the Amazon science department person who worked on this approach, sort of the package, demonstrating that with varying degrees of inaccuracy in the graph, it'll still hold. But there's a point at which it breaks. I mean, it's just, at some point you achieve garbage, and it's hard to get any signal out of that. So a good dependency graph is a must-have. And our organization is on a journey to adopt OTel, Open Telemetry, which will give us really fine-grained understanding of this call is being made here to here to here to here to here with this latency, with the status code. And once we have that, you essentially will have the perfect dependency graph. It's a journey, though. So, question, yeah.
How do you get that, other than documentation and reading the code?
How do you get the what?
How do you get the telemetry graph?
You instrument your microservices. So with OTel, you essentially insert some code into every API in your organization, which will essentially, every request gets a little tag with it, kind of tracing it along. So this is the span here, just here to here, and here's the trace. And it's collected, and aggregated. And so it's automated in a sense, as long as the engineers are able to instrument their APIs. With all things, standardization is sort of like the foundation of doing anything useful. And so if you can't get the teams across your org to adopt that, then, you're shit out of luck, essentially. Another limitation here is this can be computationally intensive. So at Capital One, we are working with thousands and thousands of microservices spanning the bank, credit card, automobile insurance, the entire landscape, right? Authentication services and so forth. I think any heuristic you can apply to reduce that problem space and make the graph smaller at the start is going to be helpful. So if you're able to say through some mechanism that, okay, we have a graph of 10,000 nodes of APIs talking to each other, I think the problem resides in the subgraph of 100, because everything else here looks good. You'll do yourself a big favor in terms of computational intensity. So we're playing with approaches like that to sort of simplify the problem space a bit. And then as far as the future goes, thus far we've done some back testing on some recent historic high severity incidents, and the results look quite promising. We're just going to continue with that and along our OTel journey, and the hope is to get to a place soon, in 2025, where we have a very good dependency graph across the enterprise and can roll this out in an automated fashion and quickly understand roughly where the problem is occurring. So that is all. Any questions? Yeah.
Do services like Datadog help with some of this?
Sorry, what was the question?
Do services like Datadog help with some of this?
They can. I think services like Datadog, New Relic, there's a whole suite of observability tools. A lot of them are dashboard type visualization tools. And they're good for manual work. They're good for manual debugging, but again, you're working with teams of 50 people who are sifting through tens of dashboards trying to triangulate the cause. We're of the mind that we can automate this process and just clearly give that team a signal in a few minutes, like, hey, look at these 3 APIs we highly suspect are the root cause. We can accelerate that process. So I think there's still a place for those services. You still want people visualizing and exploring manually, but I think we can really boost the process along with something like this. Yeah. Sorry. Yeah.
Just out of curiosity, how long did it take your team to develop that dependency graph, and how long did it take you to develop the entire process of it?
Dependency graph is the hardest part. It's probably going to be the hardest part in any organization, honestly, because it requires standardization across all the teams. It requires teams to centralize what they're calling and sort of just a lot of standardization and centralization. It's a journey that we're still undertaking. So currently at Capital One, we're using a sort of registry of APIs that are sort of known to talk to each other. However, there are unregistered APIs. That's a problem. With OTel, that problem will be solved. I mean, if we make it sort of an enterprise requirement to instrument your software with OTel, we will definitively know what is calling what and what is being used. But that is the Achilles heel, and that's the hardest part, I think, probably. Yeah.
Like, just
But-
roughly.
Roughly, so, I mean, something like that, depending on the size of your organization, can take months to years. I mean, if you're working at a 100,000 person organization, asking every single development team to instrument their APIs with OTel, it's going to take some time. They have competing priorities, right? But this approach in and of itself, the algorithm itself, it was relatively straightforward. I mean, we were able to come up with a prototype within 2 weeks or something like this, and then back testing it is a few more weeks. So the approach itself, the modeling approach, not hard. The challenge is the instrumentation and working with teams across your organization to generate that graph. That's the hard part.
Thank you.
Yeah. Yeah.
I don't know if maybe with those dependency graphs you're mentioning, if you're able to also maybe get like timestamps, right? And if you were exploring maybe like a time series problem.
Yeah. That is part of the thing here. We have to take this raw observability data, which just comes to you in the form of, hey, at 10:51 and 29 seconds, we got a 2xx call. You have to take that raw data and aggregate it into 1 minute or 5 minute time metrics, aggregations. That's sort of like the raw data to work with that we need. You can't take the individual logs and just use that essentially. You have to do some sort of aggregation, yeah. Yep.
One of the very first frames you had showed like your microservices. It looked really crazy, right?
Yeah, I think the word hellish was used.
Yeah, hellish. So I'm kind of struggling to believe that you guys are truly acyclic based on what I saw there. So like, how do you deal with cyclical microservices?
Yeah, it's true. So in the services we've seen thus far, cyclic sort of patterns are not as common as you might think, actually. In the cases in which they do occur, it's often very small cycles of sort of like this node calling this, calling that, and sort of repeating. I don't think we've seen many instances in the full like enterprise data of like a 30 length sort of cycle, which would really complicate things. I mean, that's one of the other assumptions of this, is it's working with DAGs. Another thing I would say was I went into this naively thinking, okay, if each of these is an API and the red ones correspond to broken APIs, I'm just going to look for the highest up one. Like, I'm assuming the most parent broken node is going to be the root cause. It seemed intuitive to me, but I've been disabused of that. So there's a lot of complications to this, right? Sometimes APIs appear broken, but it's sort of just coincidental. There just happens to be a spike in some aspect of its golden signal. Other times, something breaks, and then very quickly an engineer does something manual which breaks something else. And so it's hard to disentangle all of this. And so it turns out you can't just look at a graph like this and say, okay, well, duh, that's the root cause. It requires a lot of sort of understanding of the relationships and so on. Yeah. And I should also say, you don't necessarily have to use linear models between all of these things to make the predictions. You can use nonlinear predictive models to sort of structure these relationships, which can help a lot with the seasonality you mentioned earlier. So, yeah.
I have a question about this. With this complicated model, is there a way of sort of combining every like subsets into sort of one node if they don't communicate with any other? Like I don't know if you do that kind of thing.
Oh, that's interesting. So like logical units of APIs that could
Yeah.
sort of be thought of as one.
Yeah.
Yeah, I mean, I suppose you could if the challenge there, I would imagine, is just sort of getting that SME knowledge team by team and sort of, I mean, we have to interview thousands of teams essentially and sort of say, here's the map, which can we consolidate?
Yeah.
But if we could, then yeah, I suppose you could, yeah.
What if you have like a third-party APIs in your graph in the node where you cannot check that?
Yes, yeah. So that's an interesting question because you know, we rely on things like Salesforce and Zelle, right? And so as long as we have a node which serves as a gateway between that third party and our system, which we have to have, we can see the root causes occurring at that gateway node and then infer, okay, something is off with Zelle. And in fact, we saw that recently and then went to downdetector.com. Right? And there was like complaints happening an hour before the Zelle incident. So you can sort of piece together what's going on there. Yeah. Yeah.
If you have a node somewhere in the middle of the graph that's breaking, so it's not calling the child nodes.
Okay.
So you have to disambiguate between no responses coming from those nodes because they're just not even firing versus due to something breaking ahead of it or versus just not being called in the graph at all. Does that make sense?
Gotta confess, I'm not.
So, like so if you have an API now that's not surfacing any status codes at
Okay.
all,
It's
because
just-
something downstream.
It's gone radio
is breaking.
silent.
No, just because it's not even something ahead of it is breaking.
Okay.
So the calls aren't even making it there to
Okay.
get a response. How do you handle that? Like, do you need to, in terms of your calculation,
Yeah.
you just treat that as zero or as a?
I think it's a matter of what was the dynamic like in the sort of pre-incident data, and can we learn? Okay, this particular node just happens to rarely make downstream calls, or something like that. Or under these conditions with the upstream nodes, you know, when it gets these sorts of inputs, it'll make a call rarely. But under these other conditions, it will make a call or something like that. Then, if you can learn that, then I think you can work with it. Yeah. But if you can't learn on that, then that's going to be a complication. Yeah, for sure.
Any more questions? Well, you will be around the entire day, right? Yeah, so you can ask questions later on whenever it's convenient for them. And yeah, thank you so much for coming here. Ronnie, Adi, I misspelled your name previously, sorry about that. And Ethan, thank you so much for coming here.